Welcome to this explainer, where we're going to crack open the control engineer's diagnostic toolkit and demystify exactly how we test process dynamics. Look, if you're studying process control, you've probably stared at a ton of complex block diagrams and heavy equations, right? But today, we're taking all that math and grounding it in reality. We're going to look at how we safely and effectively probe industrial systems, like massive chemical reactors or HVAC systems, to figure out exactly how they tick. So here is our roadmap for today. We'll start with meeting your control inputs, then break down the step input, the impulse input, the linear ramp input, the sinusoidal input, and finally wrap it all up by building custom inputs. All right, section 1. Let's meet your control inputs. In the world of process control, you're going to hear the term forcing function thrown around a lot. What is it? Honestly, a forcing function is basically just a highly precise poke that we give to a system, so we can watch exactly how it reacts. We absolutely have to know how a system responds to changes before we can even think about designing a controller for it. So by hitting it with these specific, mathematically defined input signals, we can predict exactly how a system will act when random disturbances hit it in the real world. Let's dive into section 2, the step input. The step input is all about the sudden shift. Imagine you're out on the plant floor and you just instantly crank a flow valve open from 70% to 80% and then, you just leave it there. That instantaneous, sustained change to a brand new level, that's a step input in the real world. And honestly, it is the absolute easiest forcing function to create physically. And here's exactly what happens when you make that sudden shift. If you check out this graph of a gravity-drained tank, you can see on the bottom axis that the controller output steps up instantly from 70 to 80. Boom. But look at the top axis, the actual measured process variable. The tank level doesn't just teleport to the new level, right? It responds by gradually climbing, forming this really smooth curve until it eventually levels out at a new steady state. We call this the process reaction curve. Now, you really don't need to do any heavy calculus to grasp this. Just remember the step input's mathematical signature. We usually write it as U of t, and its Laplace transform signature is super simple. It's just A over S, where A is simply the size of the step you made. This little signature is your absolute baseline for figuring out a system's limits and grabbing that process reaction curve we just talked about. Moving right along to section 3, the impulse input. Now, notice the stark contrast here between these two. While a step function shifts and then holds that new value forever, an impulse is totally different. It's an extreme, massive spike that vanishes just as quickly as it showed up. Mathematically speaking, it's an infinite spike with a time duration approaching literally 0. Physically, creating a true, mathematically perfect impulse input is basically impossible because, well, you can't do anything in 0 time. But you can think of it like instantly dumping an entire 55-gallon drum of chemicals into a large storage tank all at once. It's a massive, idealized jolt to the system. So while a true impulse is a mathematical idealization, represented by the delta function with a Laplace transform of just A, we approximate it out in the field with a super fast pulse. Picture injecting a volume of fluid over just a fraction of a minute. We use this specifically to test a system's extreme disturbance recovery. Basically, how fast can our tank absorb that 55-gallon jolt and get back to normal? That's what the impulse tests. All right, section 4, the linear ramp input. So instead of a sudden jump or a crazy massive spike, a linear ramp input increases, well, linearly over time. It's the steady climb. Think about heating up a huge industrial oven. You definitely don't want to blast it instantly. You want to raise that temperature by a nice, steady 10 degrees Fahrenheit every single minute. The crucial thing to watch here is how the system actually keeps up with that steady climb. If you look at these two lines, the top one is our input, the steady climb. The bottom curve is our actual output. Notice how, after an initial curved adjustment period, the output eventually climbs perfectly parallel to the input. But there's a catch. Check out the gap. The output always lags a bit behind the input. Its mathematical signature tag is b over s squared, where b is just the slope of your climb. And what's super useful here is that we can predict exactly how far behind the process will trail the set point. That steady state difference is simply b multiplied by the system's time constant, which we represent with the Greek letter tau. This gives an engineer the exact amount of lag they should expect when ramping a system up. Next up, section 5, the sinusoidal input. Meet the continuous oscillator. This is a wave input that cycles up and down continuously. Now, generating this physically in a fluid or temp process can definitely be trickier than just cranking a step valve, but it is incredibly powerful. This input forms the entire backbone for advanced frequency response tuning. When you feed a sine wave into a system, something cool happens. After the initial chaos settles down, the output becomes a perfectly steady sine wave too. But notice how the bottom output wave is squashed down compared to the top input wave? We call that attenuation. Also, see how the peaks of the output wave happen slightly after the peaks of the input wave? That little shift to the right is your phase lag. Okay, the essential math tag here might look a little intense. It's A times omega over S squared plus omega squared, but honestly, practically speaking as an engineer, just remember these key takeaways. The system's output will always be a delayed wave of the exact same frequency, and its amplitude ratio will always be less than 1, meaning your signal is attenuated, or basically just shrunk down. And finally, Section 6, Building Custom Inputs. Let's be real, actual plant disturbances are super messy. They almost never look like a perfect textbook step or ramp. But here's the secret sauce. By stacking these foundational tools together, we can mathematically piece together custom inputs that perfectly mirror those complex, real-world events. You can take a step function to model a sudden 5-degree jump, hold it, and then slap on a negative linear ramp function to model a slow cooling process over the next hour. By treating these signals as building blocks, you can model practically any crazy disturbance a plant might face. Which brings us to our final thought. Think about everything we just covered. If you're testing a highly volatile chemical reactor, you absolutely cannot just throw massive step inputs or unpredictable custom signals at it and hope for the best. You have to know exactly how it will react before you even touch the controls. Knowing the exact mathematical shape and the physical impact of these forcing functions is quite literally the difference between safely tuning a continuous process and blowing the lid off a reactor. Understanding your toolkit is everything. Thanks for hanging out with me for this explainer. See you next time.